Hello and welcome to the first hydrogen and low CO2 iron and steel making webinar. This is the first of hopefully a three-parts webinar series. I am Anna Voss. I am with the AIST, and this webinar will focus on iron making with alternative reductants. As with all AIST functions, we must first go through our antitrust guidelines and our anti-harassment policy. If I can get my screen, there we go. So, do not discuss with others or your own or competitors pricing or pricing procedures or anything that might affect prices such as costs, terms of sale or profit margins or anticipated wage rates. Do not make statements about your own prices or those of competitors. Do not talk about what individual companies plan to do. Hold on one second. In particular markets or with particular customers. Do not disclose to any others or any competitively sensitive information. Do not propose or agree to any action intended to disadvantage or injure another company. Do not stay in a meeting or activity where any such anti-competitive talks occur. In our anti-harassment policy, the Association for Iron and Steel Technology is dedicated to providing harassment-free environments for everyone, regardless of age, race, religion, disability, gender, gender identity, or sexual orientation. We do not tolerate harassment in any form of anyone attending an AIST event. Harassing behaviors include offensive verbal comments relating to age, race, religion, gender identity, or sexual orientation. The use or display of sexual images, activities, or commentary in public spaces, deliberate intimidating, stalking, or following, harassing photography or recording, sustained disruption of events, or inappropriate physical contact. Participants asked to stop any harassing behaviors are expected to comply immediately. Participants violating this policy may be sanctioned or expelled from the event or the membership at the discretion of the AIST leadership. So with this with this webinar, we have a lot of participation from those in South America. And I just wanted to point out one of the programs that we have available for those that it's our ABM AIST combination membership. So if you're a member of ABM or AIST, you have the opportunity to get membership to the alternate society at a reduced rate. And if you're interested in that, take a look at aist.org/ABM. And then a few notes for this webinar in particular. So right now, all of the attendees that are out there, your audio has been disabled. And if you would like to ask any questions to the panelists, please use the question and answer function that's here within the webinar feature. If you move your mouse around, you should have a menu that pops up and you'll see both the question and answer and the chat function. Please use the question and answer feature to ask questions to our panelists. Our hosts and moderators will determine which questions are presented to the panelists at the end of the webinar, assuming we have enough time to get to audience questions. Also, this session is being recorded, and if you have any technical difficulties, email training@aist.org and we'll do our best to help you out. So with that, I would like to introduce our two moderators for this session. Chris Pistorius is the POSCO Professor for Material Science and Engineering and the co-director for the Center for Iron and Steelmaking Research at Carnegie Mellon University. He's also the current chair of the DRI Technology Committee. And Zane Voss, who is a metallurgist with CIX LLC, and he is the current education chair of the DRI Committee and the most recent past president of the DRI Committee. So with that, I will turn it over to Chris and Zane, our moderators, to introduce our four panelists.
Thank you very much, Anna. And from my side, welcome to everyone. I am Chris Pistorius, as Anna said, and for this year, I'm the chair of the DRI committee. This webinar is one of the activities of our committee, and anybody interested in direct reduced iron, you are very welcome to join us. But today we have an excellent lineup spanning the globe, as you can see, of speakers who will talk to this particular topic of iron making with alternative reductants. And I'll briefly introduce each of them and then ask them in turn to give their presentations. The format will be each of them has a small number of slides to outline their particular take on different reductants. We, as the moderators, have some tough questions to ask them after that. And then we'll have, I hope, some time for audience questions as well. So as you should see on your screens, the speakers are Vincent Chevrier, who is with Midrex Technologies, Stefano Maggiolino of Tenova, the other producer of direct reduced iron technology, Jan van der Stel from Tata Steel in the Netherlands, who's been really driving their ironmaking research, and Jose Noldin of CSN in Brazil, who's, as I think many of you know, very active in IBM, and we'll talk to their particular take on using a different reductant than coke. So I'll just ask everyone to go ahead and give their presentations. I'll just do a little bit of continuity in between, but let's get right stuck in. Vincent, you're welcome to. Go ahead.
All right. Sorry. Now can you hear me? Okay. Thank you. So yeah, good morning, or good afternoon, or good night, wherever you are in the world. It's a privilege to be here today and presenting such a wide audience. So I was just looking at the number count. It looks like it's about 430 people now, which is great attendance. So my name is Vincent Chevrier, and I represent Midrex. We are the global leader in direct reduction. We own and license the Midrex process, and we also support the plants that are built with a variety of services. We are headquartered in Charlotte, North Carolina, and we have offices in different parts of the world. And we are a wholly owned subsidiary of Cobelco. I think my video shows a picture of our plant in Saudi Arabia. So I am not in Saudi Arabia right now. I am in my home in Charlotte. So one slide. If you're not too familiar with direct reduction in the Midrex process, so here I'm going to present a brief overview. You should see my pointer here, hopefully. But in the shaft furnace, which is that part in the metal with the kind of the rusted color, it produces metallic iron from iron ore. So we feed iron ore from the top, and it comes out as metallic at the bottom. The reduction happens inside that shaft furnace here with a counter current of reducing gas, which is mostly hydrogen and CO. The feed material can be iron ore pellets, iron oxide pellets, DR grade or BF grade, and it can also be iron ore. The products coming out, there's a lot of different options, but it could be cold DRI, it could be hot DRI, and it can be HBI or a combination of these different forms of product. And it's really a function of where it's going to be used, what's form it is best. So the Midrex process is also very flexible in terms of reducing gas sources. The most common is natural gas, which is what we call the Midrex NG plant. In this case, natural gas goes into the Midrex reformer, and it comes out of the reformer and it goes into the shaft furnace with about 55% hydrogen, about 35% CO, at about 900 degrees C. But we have had Midrex plants that have been designed for different types of gases, like coax gas is pretty common, coal gasifier is one of them as well, and even steam reformer. So you can see we've had different composition of gases with hydrogen CO ranging from 0.4 to about 3.5. As of now, there's been about 100 Midrex built around the world. And we have plants that have done just about all of these combination, if I can stop clicking. And the newest plants are rated for about 2.5 million tons. So it's about the size of a blast furnace. And speaking of blast furnaces, I want to point out two additional points regarding flexibility compared to blast furnace. Is one, that the Midrex process has the ability to reduce its output to meet demand if needed. So it's been reduced typically to 30% of the, we can decrease the output by about 30%, but some plants have achieved 50%. And second is that the plant can be idle for short periods of time and still hot, and therefore they can be restarted very quickly. And if we need longer stoppage time, it can be cold idle. But even in that case, the restarting of the plant, meaning making good products, on-grade products, is a lot faster than a blast furnace. So I know the title of the webinar is Ironmaking with Alternative Reductant, but really what the main discussion is going to be around hydrogen. So we've been working for several years on an adaptation of the Midrex process to green hydrogen, and we call it Midrex H2. We believe that advances in green energy and power generation and in hydrogen generation from electrolysis can be a game changer for the industry. Until recently, direct reduction was really limited to places in the world that had natural gas, but hydrogen can be produced pretty much anywhere in the world. So the main driving force for this transformation is going to be CO2 emission and their reduction. And it's generally accepted that the only technology that's proven that can meet the Paris Agreement for CO2 reduction is hydrogen direct reduction coupled with an EAF. Nowadays, many countries have their own hydrogen roadmaps, and I've looked through some of them, and every single one of them that I've seen, U.S., Germany, Australia, they talk about hydrogen DRI as the way to achieve those CO2 emissions, and even the IEA, the International Energy Agency, their technical roadmap for hydrogen reference direct reduction with hydrogen. So it's really accepted that it is the promising technology for reducing CO2 emissions for in steelmaking. Of course, there's some limitation in some challenges for the adoptions, but the direct reduction itself is not one of those major challenges. We've made a short video. It's about 4 minutes long. I don't have time to show it today, but here's a link to the video, and it kind of highlights how we view that transition. And I really encourage you to get on the Midrex website and view that video. It's really well done, and the team put together something that we're really proud of. So this is the main slide, and it's kind of the summary of what that video shows, which is that transition from a fossil economy to a hydrogen economy, and how the Midrex process can be adapted to switch from natural gas to hydrogen. So with the Midrex process, it's by itself, it's possible to use natural gas and reduce CO2 emission nearly by half immediately by just switching from coal, coke to natural gas. The numbers here, the 500 kilograms of emissions, that might seem a little low for people that have looked at these numbers, but here for illustration purposes, I just put strictly the emission from the Midrex plant, so they are really scope 1 type of emissions. So as hydrogen becomes available, and we can inject hydrogen into the Midrex process, and we put down 3 cases again just for illustration purposes, and the numbers are just kind of rounded numbers again for discussion. But the first thing you'll see is that the amount of hydrogen in the reducing gas, go from 55% to 62, 72, 77%. So these are actually pretty small transition in the composition of the gas. So that's why we're very confident that we can use these gases for direct reduction, because they're not really drastic changes from what we do typically with a Midrex NG plant, and definitely well within the range of what we've done with other technologies. You also notice that the carbon in DRI is decreasing as you put more hydrogen, and that's strictly because we're putting less carbon molecules from CO and from methane into the process. So there will be less carburization done. In the Midrex NG case, we use our ACT technology, and we can go up to about 4% carbon. We can use that technology for higher levels of hydrogen, but as we put more hydrogen, it becomes less and less efficient, and we're looking at ways to put carbon in DRI in more efficient way than with ACT. The last stage is that 100% hydrogen case. So when hydrogen is available, large volumes, it's cheap, existing plant can still be converted to a 100% case. And in the case of a new plant, it's actually a simpler type of process flow sheet. So if we design a plant strictly from the beginning with 100% hydrogen, it will be a little bit simplified flow sheet. The case on the right-hand side, the Midrex A2 100% hydrogen, is the design that we're working with ArcelorMittal in Hamburg to demonstrate that is absolutely feasible to produce large quantities of DRI with 100% hydrogen in an industrial scale. The next slide here, this is an illustration of the Midrex process. So again, we've changed our existing flow sheet that we were presenting before to this kind of simplified format for easier understanding. But the hydrogen is injected into the process loop. And the location can change, but this is a good place to hide the hydrogen. And as we go higher in amount of hydrogen, we have to have steam in the process, and it's mostly to protect the reformer. So there's a transition point at which steam needs to be added, and the steam can really come from other part of the plants. If you're an integrated plant, it can come from heat recovery types of system. It can come from auxiliary boiler. It's a low pressure steam, so it's a very simple technology. Also, the hydrogen itself can come from many places. So it could come from a pipeline. It can be green hydrogen if you have access to it. It could be any other color of hydrogen. You know, for direct reduction, a hydrogen molecule is a hydrogen molecule. It doesn't matter where it comes from. So we can use it either way. And this type of flow sheet is great for that transition phase, because the amount of hydrogen that we can add, you know, is likely to fluctuate depending on where it's coming from, especially if it's coming from solar or wind power, and the process itself can tolerate these fluctuation in hydrogen content. So these are the two options that we have for Midrex process with 100% hydrogen, and it really comes down, the difference is where the hydrogen is coming from. So again, if it's coming from, you know, we call it over the fence, meaning it's coming from, it's added to the Midrex loop from an external source, and that really, it could be coming from a pipeline and distributed network mixed with, you know, some, you know, from the grid basically. Or if you have electricity available, it can be located on the site right next door. It's the same kind of integration. So if it is on site with the plant, there is some integration that is possible. There are some hydrolyzer technologies that can be better integrated in the flow sheet, especially solid oxide electrolysis, because it operates at higher temperature and low pressure, which are very close to the Midrex process. So if that's the case, we can do a little bit more process integration or optimization of the whole system with that type of unit. But really, it doesn't matter where the hydrogen is coming from. We know that you can reduce iron ore, and really that selection, whether we use over the fence type of design, we use integrated type of design, it's more function of what is available at that particular location. So we're not really selective on any type of electrolyzer technology. Hydrogen, you know, depending which one we want, there's pros and cons. So the last thing I want to point out from this slide is the hydrogen consumption. So again, for a plant that's about the size of a blast furnaces, you know, we need about 13.5 tons per hour for the direct reduction, which is about the equivalent of, you know, 800 megawatt electrolyzer. These numbers are very, very approximate, but the point is that direct reduction with hydrogen requires a huge amount of hydrogen that is not currently available. In our process, we make it from natural gas directly from the Midrex reformer, so we have access to these large volumes of hydrogen. The electrolyzer technology is not at that scale yet. So as a conclusion, what I really was trying to show that is the Midrex process is a proven technology, first that can be used today to immediately reduce CO2 emissions using natural gas, but it can also be the bridge technology as hydrogen becomes available in larger scale. So it will take years before we can get the volumes that are needed for 100% hydrogen, but it is absolutely possible to build a plant today using a little bit of hydrogen and more as it becomes available. And basically that plant will be ready when hydrogen economy rolls around. Our oldest plant is in Hamburg. It was built in 1971. So these plants are really designed to last for a long time. So we think the flexibility of the process make it very suitable for that transition. And like I said, it's very suitable for the variation of hydrogen availability that we expect, especially if it comes from solar or wind power. I didn't discuss much of the obstacles for adoption, and that may come up during the Q&A. But really, ultimately, it is about the cost and availability of hydrogen. But really, the cost, that cost and availability is especially driven by electricity generation. So, you know, this hydrogen flow sheet, or using hydrogen for direct reduction at scale is not going to be feasible until the cost and availability of CO2-free energy is at the scale that we would truly need. So as a conclusion, first of all, I just want to say thank you for listening and for attending. There might be some questions that will not be addressed from the Q&A, so you can email me directly. My email address is on the slide. And also I want to put the link to the Midrex video. Again, I strongly encourage all of you to take a look at it. So with that, I'd like to conclude my talk. Chris, I will hand it back to you.
Thank you very much, Vincent. We'll move on to Stefano Maggiolino for his presentation, the Tenova view on that. Stefano, please go ahead.
Yes, good morning, everybody. I would like to thank AIST and the chairs for the opportunity I've been given for explaining the energetic technology and its contribution to the decarbonization of the iron and steel industry. Together with Daniele, at Tenova, we keep innovating the Energiron direct reduction technology on the base of proven and reliable solutions. In particular, at Tenova, sustainability has always been a pillar that supports every project that we undertake. And we have invented this neologism that blends the Tenova brand, sustainability, so the Tenova brand, our eco-friendly values, and the capacity to deliver sustainable solution. And you may see most of our case study best practices in the platform sustainability.nova.com. Let's go to the technical part. You can see that the energetic technology has three ingredients. They made us the right solution and benchmark for decarbonization of ironmaking. The three ingredients are: first, we have an intrinsic CO2 absorption plant in our process scheme that allows to have selective removal of CO2 and the capacity of CCU and CCS. The second part is the capacity of producing high carbon DRI. We're the only one that have produced tens of millions of tons of high carbon DRI, and we will see how this contributes to the decarbonization of the industry. And the third one is the flexibility. As you may see from the process scheme, the same identical scheme is used for any makeup gas, so natural gas, reform gas, coke oven gas, hydrogen, a mix of all the above, and also transitioning from one to the other, and also for giving flexibility to the product itself. But let's start from the removal of the CO2. Let's say if we consider just a simple carbon mass balance, we see that when we put carbon inside the circuit, we have three ways to eliminate the carbon. The first one is with the product. The second one is through emissions into the atmosphere. And the third one is with the sequestrated emission, where we are the only technology that at the industrial level since decades, we selectively remove CO2 up to 62% of the produced CO2. We're talking about approximately 260 kilos of selectively absorbed CO2 per ton of DRI. And so if we see our users, it's no wonder, for example, that Ternium, it's 30 years that they've been selling CO2, and it's no wonder they've been nominated again this year as sustainability champions by the World Steel Association. Definitely their capacity to sell selectively removed CO2 is a component for them to get this very important prize. As well for Emirates Steel. Emirates Steel, last week, it was the World Environment Day, they highlighted that their capacity of CO2 usage for enhanced oil recovery. So at the end, for our users, CO2 is no longer a burden, but actually is a source of pride and source of revenues. Said that, we see how the quality of the products may contribute to decarbonization. It said we are the only one that have proven capacity of producing high carbon DRI, and high carbon DRI at the end, when we talk about 4 to 5% carbon, at the end it's pig iron with some gang. So blending, putting together our DRI technology and our smelting technology, we can produce pig iron directly by charging high carbon DRI to a melting unit that basically just removes the gangue, and we have a hot metal. In this way, this solution can definitely substitute the blast furnace iron making with a dramatic reduction of CO2 emissions. Just imagine one case that a blast furnace is to go under relining, but possibly the right solution is to move to this DRI hot metal production. The good thing is that all the downstream plants, so I'm talking about the steelmaking plant with BOF, will remain exactly the same. So we can tap hot metal from a DRI smelting unit directly in the torpedoes and have all the downstream capacity as they are. If we move then to the flexibility of our source, as I said, our process scheme can work with any reducing gas that is connecting basically to the pipe. And specifically, we can tap also hydrogen coming from electrolysis through renewable electricity. So we can have a plant, an existing plant that works with natural gas, and we can start injecting hydrogen as it becomes available and moving up to 100% hydrogen without any special device. In particular, if we see our experience with hydrogen, let me say that steel making with the DRI has always used hydrogen. But in our case, particularly since the 50s, we've been using steam reformers. In the plants with steam reformers, we achieve a gas composition that has approximately 70% hydrogen in the process gas. So we have this scheme that is naturally fitted for hydrogen. We have this experience, but specifically in the 90s, in our pilot plant that was producing 36 tons per day of DRI, we did campaigns with 90% hydrogen. This test provided all the information that we needed to define the process and design parameters. So like flow temperature correlation, reactor LND ratio, operating pressure, solid resistance, etc. So we have all the data to design correctly. We already have this data to design correctly a plant that can work without any problem with 100% hydrogen. Also from the mechanical viewpoint, we have the equipment that has already been working with a very high percentage of hydrogen in our industrial plants. And if we see from an energy point of view, we can see in the first graph that the energetic process with hydrogen has 6.6 gigajoule per ton of DRI as hydrogen, plus an additional 1.6 gigajoule per ton of DRI as a fuel. So this is very low also because we take advantage of the high pressure characteristic, let's say a high pressure condition in our scheme that is very beneficial when we treat with a very low density gas as hydrogen. And we can see on the right how increasing, let's say, the percentage of hydrogen in the gas, in this case, in terms of energy, we definitely abate CO2. Because of these reasons, we've been selected by Hybrid, the Swedish initiative for hydrogen Ironmaking. And we are now in the training and starting the commissioning of the plant. We have supplied all the main equipment, so reactor, process gas heater, sealing valves, etc. We're very proud. This picture was taken during an interaction with our team and together with the Hybrid team a few months ago. And also we're working with Salzgitter, where we partner for their transition project. So you can see from this graph how the idea is to start removing blast furnaces, shutting down blast furnaces, and converting their plant to electric steam making with DRI produced via hydrogen. In order to summarize, let's say, the benefits of our technology, we can see if we make 100 the CO2 emissions of a blast furnace together with the BOF, we do have some small gain by adding DRI or HBI to the blast furnace. But really, the big change is when we move to melting DRI, either in a melter for production of hot metal or in EAF to produce steel. And together with our capacity of CO2 selective removal and commercialization, we are the benchmark in terms of CO2 emissions for the ironmaking industry. So this is a typical case where in a location like maybe in Europe, where the carbon footprint is 0.5 kilos of CO2 per kilowatt hour, with our standard technology with natural gas, we can achieve less than half of their CO2 emission than a blast furnace, and of course even lower, much lower with using hydrogen. hydrogen can reach to 100%, of course, but we consider that there is let me say, a sweet spot where there is a balance also from the carbon that is needed in the steel for the final reduction of iron oxides. With this, I've finished my presentation. You can follow us in our site, www.energino.com. And again, thanks to AIST for the wonderful opportunity.
Thank you very much, Stefano. We'll now move from direct reduced iron to producing liquid iron for a presentation by Jan van der Stel, who's really been very closely involved in the development of the HYSARNA process. So Jan, please go ahead.
Okay, thank you, Chris, for this kind introduction. Can you give me feedback that you see the slide?
Yes, it works.
Okay, thank you. Now, it's a great pleasure for me to give this presentation on behalf of Tata Steel to the DRI committee on the developments of the HYSARNA in Tata Steel. And I would like to give you all, to say to you all, good morning or good afternoon, and perhaps you're already asleep, so also then also good night. And this presentation I make together with my colleagues Koen Meijer and Tim Peters, who are also heavily involved in the HYSARNA process. What is HYSARNA? The HYSARNA development is that we compare this with the conventional blast furnace route. When iron ore and coal are coming to the steel making site, then you need the coking facilities, and you need the agglomeration, so the sinter making, and you need the pelletizing, and then you go to the blast furnace, where then you produce the hot metal. In HYSARNA, let's say we skip the complete coking and agglomeration steps. Iron ore and coals are directly injected into the HYSARNA vessel, and then we make use of the, let's say, the fine ores and the coals. So in principle, no agglomeration and coking is necessary. And the same hot metal is produced and can go to the steel shop. What are the benefits of HYSARNA? I think HYSARNA has been said that it offers a high level of economical and environmental benefits, because when you look at the economical benefits of the process, which has been developed at Tata Steel already since the 80s. Let's say the Ironmaking, you can process it with low-cost raw materials. You can use non-coking coals and also and low-grade ores. You can use recycled waste oxides, slags, and galvanized scrap. And this has been processed in the pilot in IJmuiden. You have a very high energy efficiency, and you can have greenfield developments, so you can have much lower capex. The environmental benefits are that you have lower CO2 emissions. There will also be lower SOx and NOx dioxides and fine dust emissions, and you will have an avoidance of dumping slags and dusts, and you can use mineral reverse. If you do a benchmark of the process, and this has been done in the ULCOS project. ULCOS is the European Initiative for Ultra-Low CO2 Steelmaking. And when you compare the HYSARNA with the conventional middle, let's say average European blast furnace operation, then you can see that you can have a significant lower CO2 emission based on let's say what has been done in ULCOS. But when you add scrap and biomass to the process, you can go further down. And when you do a combination of that, you can more or less come to let's say 1,000 kilogram of CO2 emission compared per ton of hot metal compared to the 180-20 of the conventional blast furnace. Now, this has been put forward. This was a scenario analysis, and then the pilot plant was designed at the IJmuiden steelmaking site, and there we have had several campaigns. Let's say those campaigns were first part of the ULCOS consortium, and there, let's say, there the plant was erected and was designed, and in 2011 we had the first metal tap. Then, let's say, there was that was in the first campaign. Then in 2012 we went into the second campaign, that we had a very long operational period. So that then we found out that the process is working well, and then we start optimizing it, and the first hot metal was delivered to the Voss plant. And what you see is then also that you see a gradual reduce of the carbon consumption in the process. Now, this was succeeded then by the fourth campaign, and there we already also tried recycling of scrap and high zinc oxides, and that went successfully. And at the end, we more or less came to a considerably low coal consumption rate at that campaign. Now that gave confidence to all the partners and also to Tata Steel. And then we decided to do a major plant revamp, and we expanded the plant, for example, by additioning of a coal grinding facility. And overall, that was an investment of more than 20 million euros. And in 2017, we went onwards with the development of those campaigns. And then the first goal was there to do a long duration test with of the process and of the equipment, and we would like to demonstrate that you can do a CO2 reduction of 35% without any carbon capture technologies. Therefore, we used 40% of biomass, which was charcoal with low S, low density, and this charcoal was injected to one of the coal injection lances. Also, in addition to that, 35% of scrap was used, and the scrap was considered of shredded scrap and punchings. And also this was added to the vessel by using graphite. What you also see is that you can go to quite considerably low silicium values in the hot metal, which is then delivered to the steel shop. Now, what are the tests? The test with biomass and scrap that is possible in Haizana. We demonstrated that. We collected over 200 tons of charcoal that was prepared in the grinding lines, and then in one of the injection lenses, it was added to the butt of the process. So there it replaced there was a coal replacement of about 45%, and that meant roughly 1.2 kilogram of biomass per kilogram of coal, and that had a fossil carbon reduction of about 35%. Also, scrap. The scrap was used. It was sized scrap. It was directly fed into the bath, and the combination of biomass and scrap, where we did a biomass test run of 40 hours, and in those 40 hours, 20 hours of scrap was used. We had a reduction. The biomass was roughly 43% of the fuel, and overall the scrap was 37% of the iron-bearing units, and this gave a productivity increase of roughly 40% and an overall fuel rate reduction of 23%. So the fossil carbon reduction was more or less 57%, which was demonstrated in in the pilot facility. Also, we want to go to higher levels of CO2 in the top gas. The pilot plant top gas is roughly 73% of CO2, 5% of oxygen, and 22% of nitrogen. Now, to make this CO2 more applicable for further uses, and then let's say the amount of CO2 in the gas from the reactor, which is here, need to be improved, and therefore the CO2 in the injection, the gas which injected the coal into the bath was replaced by CO2. And that was gradually increased, and you could see that at a certain moment, 85% of CO2 could be reached, and so that means that this gas is capture ready, and that is feasible. Also, what we are doing at the moment, we try to make this gas ready for usage for other purposes, like enhance oil recovery, or let's say using it for greenhouses. And therefore, as the CO2 level in the off gas is already up to 85%, it is you can do the carbon capture with the cryogenic method. And this has been proven by TNO, and TNO proved that it is possible. And therefore, at the moment, we are doing an extensive feed study to make this happen. Also, what we're doing is we are also looking at the let's say industrialization of the pilot plant, and therefore several scenarios have been calculated. Here you see the pilot plant vessel on the left-hand side, and on the right-hand side you see a demonstration plant level where we think you can go up to 1.0 or 1.5 tons of hot metal per year, and that is under investigation to be installed on the IJmuiden. And but in between, we think you need an intermediate step, and a suitable location for doing that is the Jamshedpur site at Tata Steel in India. And therefore, I think also we also think that the HYSANA demonstration plant is foreseen to be capture ready. So, and then it provides also low phosphorus hot metal for steel critical steel qualities. It enables recycling of LD slag. We produce hot metal at quite a competitive price, and it allows the connection to future CO2 capture and reduce the CO2 emissions of the site. In conclusion, the steel industry has a lot of shelf solutions available for the climate change, and also on circular economy issues. And almost every potential solution holds an uncertainty, a development risk, and an increased cost. And HYSANA is an iron-making process for a greener and circular economy. And after 10 years of development at the pilot plant in IJmuiden, let's say this is now close to completion, and scale up to industrial still holds a considerable development risk, but is also an incredible potential can be foreseen. And cooperation is the buzzword which has been the HYSANA process for all those years. It started in Ulkos, and let's say new partners in the pilot scale capture plant, which need to be constructed at the HYSANA pilot plant, are welcome, and that's possible. And if you are interested, you can contact me with my contact details are at the bottom of this slide. So thank you for your attention.
Thank you very much, Jan. Then for our final presentation, we'll go to Jose Noldin of CSN to talk about the use of charcoal to make liquid iron. Jose, please go ahead.
Can you hear me?
Yes.
Good. Just put in presentation mode. So first, thanks everyone for being listening, and also for AIST for organizing, giving us the chance to share some of our views on new reductants for Ironmaking, and especially to Anna, Zane, and Chris for putting it together. Good morning, everyone. In my case, I'm in Brazil, but good afternoon and good evening to everyone else in other regions. First, as the COVID still very present here in Brazil, I really hope you are all well and safe, including your closed ones. And I have to say it's a special feeling after so many conferences around the globe in my 20 plus years of industry. It's very interesting, this format, and I believe we should all get more used to this, and also looking from the bright side, a global attendance, that I was in a meeting before, I'm gonna finish this one and going to another meeting. So it's actually quite effective in many respects. Also wanna thank the previous presenters. Hats off to them. I know Vincent, Stefano, and Jan for so many years, and indeed the efforts, in improving our industry, it's remarkable. So on behalf of ABM, I want to thank again, and actually what we plan today is to share some views, not to close the debate, actually to enrich on how charcoal, biomass in general, can actually be an interesting help in our decarbonization efforts. That's why I like to start with a provocation. A lot of you have understood from previous presentations or conferences that yes, biomass have been used as a reductant actually centuries ago, and we still use it in Brazil for a big portion of our iron production. So in different debates and conversations, I always feel that there is a feeling that maybe it's an ugly duck. Yeah, people do iron with the biomass, but doesn't look nice. Or no, it can be really a teammate for the decarbonization efforts. And I want to strongly show my conviction that it can be a teammate. If we look at the European Green Deal, I'm in Brazil for 1 week now. It's starting in a new change, in a new challenge in my career. But I spent the last 9 years in Europe. So I have still a quite European driven view. And if I may, the European Green Deal has an ambitious target of becoming climate neutral by 2050. Other regions will certainly follow, if not already following. Yeah? And carbon neutrality based on hydrogen, I find it fascinating. It's very nice, maybe ready, as we saw from the previous presentations. However, we should not forget that vast and cost-efficient quantities of green hydrogen need to be available. Taking some numbers from other experts, we see 4 terawatts per hour for every million ton of hydrogen-based iron-making and EAF steel will be needed. Huge capex will be required. So we should not forget that a lot of money needs to be pumped in. Also taking numbers from other people, because I personally believe this is underestimated. More than €1 billion per million tons of integrated steel capacity that will be replaced. So if we take Europe, for example, where you have 100 million tons of integrated steel being produced, let's call it 100 billion euros, which need to come from the taxpayers. It's not peanuts, huh? Besides, producing hydrogen in such capacities will require a lot of extra money for the production, so the OPEX will certainly be put into a different level. And we should not forget that the iron ore pellet supply market is already tight, so new capacity needs to come online. So these are some of the challenges that I see on hydrogen, and why I personally like more like a multiple solution, not a one size fits all. Yeah? So biomass can allow ironmaking to be done on a sort of a circular CAO approach. But it's important that we look biomass iron making production beyond the eucalyptus. So this is what I'm talking about, new technologies that allow different species to be used for iron production. So, because charcoal use, as we said, it's well developed. However, there are still huge potentials for the use of a city waste or fast growing species, or even the preparation of a pre-prepared burden. For example, self-fluxing fuels to be used in different technologies.
Hey, Jose.
Yep.
I have one question. Are you sharing your screen right now?
Yes, I am.
I don't think it's visible to the attendees.
Wow. So let me see. How about now?
Nope.
And if I, let me do this. Thanks, Anna. Yeah, but I was sharing before. Let me do it again. How about now?
Yeah, now we see it.
Okay, so not so bad, not so bad. Let me, I need to, there is a small button here. Yeah. Good. And now, still there?
Yes.
Okay. Sorry for the trouble.
But
yeah,
now
you
we see it in presenter mode.
Yeah. But you see only one screen, right, or not?
Now we see two slides at the same time.
What should I do here? This one?
Sure,
No.
try it.
This one?
There you go.
Good.
Perfect.
As you can see, we are all learning, me especially on this one. So we also believe that biomass and charcoal would allow fast and immediate results, which would, I believe we are all in a sort of a grace period with society. So people are still patient to what can be done to reduce CO2 in the steel production. And I personally believe we need some quick results. And biomass and charcoal can allow that. We would use CO2 actually as a raw material. So it would be a mining of CO2 from the open air to production of the biomass. Virtually no sulfur from biomass and very low impurities, which brings another additional advantage, which would be low slag rates. I also believe we need to recognize that some bad examples exist, and these need and can be stopped with the deforestation, for example, pollution in the production of charcoal, use of old technology, and etc. These are still there, and we need just to fight them. Taking a specific case in Brazil, just to put some numbers, iron making in Brazil, we have today production last year was 30 million tons, of which 1/4 was based on charcoal, so quite well established. And there is a very recent study made from the Industry Federation in Brazil in last February, where all the life cycle analysis was done, and with update techniques and so on, taking good examples with all included, transportation, effluents and so on, actually in the production of iron using charcoal and biomass, there is a release, instead of capture, there is a release of close to 2 tons of CO2 per ton of pig iron. So it's the opposite, we release. So we actually release oxygen and capture, sorry, this is wrong, not release, there is a capture of CO2 of 1.85. And we see just some good examples of, this is from ArcelorMittal Bioflorestal. So you see a very high-tech production of charcoal. And some other projects in the world, for example, ArcelorMittal with the Torero project, where they plan to make biocoal to inject in, or use in different ways in the blast furnace, as well as SSAB with the BioStart project, where they actually made a few tests and showed to be technically feasible to use biocoal as a PCI replacement. And that will bring, again, immediate results, which can be quite interesting. And my favorite, of course, in Brazil, Tecnored, where actually carbon can be used as a reductant and also as a fuel, using different species, different sources of wood different sources of waste streams or food residues that can be used to be carbonized, generating green carbon to be used as a reductant, but also as a fuel in this novel technology, which is currently under industrial implementation. So I see these are just a few examples that go beyond the eucalyptus or even beyond the mini blast furnace, which is so well known in Brazil. And again, to wrap up my presentation, the idea that we want to put forward and share with you guys, it isn't that charcoal and biomass can be the one solution for lowering CO2 in a steel production, but we actually believe that if well played, biomass can actually be introduced to contribute to the decarbonization efforts. And making a little bit of advertisement, this is actually what we want to discuss a lot at the next International Conference on Energy and Material Efficiency and CO2 Reduction in the Steel Industry, which will be held in Brazil in 2022 within the ABM week. And this is a well-established conference after Germany in 2011, UK 14, and Japan in 2017. And with that, I hope to convey, let's say, these last remarks on biomass, charcoal, and finish my presentation. Thank you.
Thank you very much, Jose. And thank you also to all of our presenters. The plan here is to keep going for another 10 minutes or so with some questions to the panelists now. I'll start with the first one, and after that, Zane Voss, my co-host, will take over. So just as a first question, which I'll put to Vincent Chevrier of Midrex, is just to give us a little bit of a more detail on how you are working with other companies to actually implement this technology.
Yeah, thank you, Chris, for the question. So, I mean, of course, you know, Midrex, we're a fairly small company, and we really have, you know, we're the expert in direct reduction, but we really don't venture outside of direct reduction. So we will absolutely rely on partners, including some of our construction partners, to work on the implementation. So there are pieces that are definitely outside of our scope of expertise. Hydrogen generation being one of them. So that's why we're not really tied up to a particular way of producing hydrogen. We're just more focused on how to use the hydrogen when it's available, and then our partners or you know, we can look like at different solutions and find out which one works best with our partners. So it's really more for team approach, and it will take you know, it'll take some time to get there.
Okay, thank you very much. I'll hand over to Zane now to continue with questions.
All right, thank you, Dr. Pistorius. Before I ask the next question, I did want to make a comment that in the Q&A, there were a lot of different questions related to the impact of say, hydrogen iron making on the steel making process, and also production generation of hydrogen itself. So right now our plan is to have 2 additional webinars in the next month or so. One focused primarily on the generation of hydrogen, and the third, the last of the series of 3, will be focused on the impact to the steelmaking process itself. So a lot of those questions will be answered in a future webinar. I'm sorry we can't get to those today, but our time here is limited. So I'm going to go off script a little bit. Anna put this presentation up with some questions, but there were several questions in the Q&A related to the general energy balance of the DR process when using 100% hydrogen. So I'd like to ask Stefano, can you make some general comments on the total energy consumption of like a typical natural gas unit versus a system with 100% hydrogen?
Yes, sure. The key in the transformation, let's say, from natural gas to hydrogen, the key word is kinetics. So the hydrogen again, both from laboratory, from what you study in your chemistry book, but also what we experienced in our pilot plant in the 90s, is the best reductants available for iron ore. So although there is a fact that the reduction with the hydrogen is endothermic compared to the one with CO that is exothermic, the overall balance, let's say, if we take into account both thermodynamics and kinetics as the major impact. This is why we cut, let's say, overall energy consumption from 10, let me say, gigajoule per ton of DRI to 8 when we use hydrogen. And again, this is something that in our technology you can do with the same plant and the transformation a little bit at a time. Let's say start reducing natural gas, start increasing hydrogen at the level of the availability and the economics of the plant.
All right, thank you for your answer. So I have a question for Jose. So you yourself mentioned that biomass, charcoal, things like this have been used for a very long time in the iron making process. So what in particular would you like to highlight that maybe you didn't cover in detail in your presentation that's new or innovative or exciting about the use of charcoal and biomass?
Thanks, Zane. Thanks for the question. I believe there are a couple of things which are, let's say, more relevant today. If we look production of iron based on charcoal, there are three main steps: the forest or the plantation, charcoal making, and iron making. I believe on the forest, there was significantly improvements. The productivity of the forest today are much higher by manyfold here in Brazil, particularly due to the pulp and paper industry, and also on the iron making. The weak link still is the charcoal making, but I see several technologies popping up. And what is making them, let's say, achieve maturity and high performance? It's a lot of technologies and knowledge and attention and dedication to their development. But certainly the big difference is the CO2 cost. So this is, making a lot of the ideas which before they were not economically feasible, and today they are much more so. Even old concepts or ideas that in the recent past were crazy, if the CO2 cost remains very high or even increasing further, this is what makes all the difference, and these old techniques can even become the good answer.
All right, thank you. So question for Jan. Tata has been involved in developing the HYSARNA project for many years, and using that as an example of a large industrial consortium. Do you feel like this type of consortium or organization is useful and a good solution to developing new advanced technologies, or is it more of an obstacle, or what's your view here?
Dean, thank you for the question. I think we already from the start, when Hoogovens and British Steel and our colleagues from Italy, Ilva, started the development. That was done in the European framework. So that was on the development of for the cyclone converter. So that was at that time already a consortium, and all the risks were more or less shared amongst each other. So tests were done in UK, in Italy, and at Hoogovens in IJmuiden in the Netherlands. And so that was all, at that time, it was already a consortium, and this consortium shared not only the costs, but it shared also the knowledge of the different technologies available at all three locations. And that is a very strong point in developing these new techniques, because everyone sees it from a different perspective, and that makes it can makes it more easily for this let's say to make this development a success. And later on, this development went on, and let's say under the umbrella of the CO2 reduction program in Europe. And also at that time, a lot of technologists from all the companies, from Tata, from ArcelorMittal, from TKS, from Voestalpine, SSAB, LKAB, all the partners at that time, they shared their knowledge, and they were available in the engineering stage, in the building stage, and also in performing the trials. And that makes it very strong, because then, let's say, you can share all knowledge of these experts in doing those tests. And also you share let's say the financial risks amongst each other to make it happen. And this is also we would like to progress this way of approaching the development of the HYL pilot in combination with the carbon capture plant. So I think it's an honor to work with those people, and I think it's very strong that the consortium work together to make it a success.
All right, thank you. So I have a question for Vincent, a technical question from Elaine Chin. She asked, for the Midrex H2 process, do you require some minimum amount of steam in the feed gas when using very high hydrogen rates to protect the reformer, or is that not required?
So in the Midrex H2 scheme, meaning that it's pure hydrogen, no, I mean, there's no steam needed or anything like that. However, the steam, the point about the steam is when you add hydrogen into the existing Midrex NG, the natural gas process with the Midrex reformer. So there is some steam that is needed to protect the reformer. So basically, we need to make sure that we have the right composition into the reformer tubes to make sure that the catalyst does not degrade from the reaction that would take place there. But it's a fairly small amount. I mean, of course, it depends on how much hydrogen you put in. And we say, you know, if we displace about 20 to 30% of the natural gas with hydrogen, below that we really don't need steams, and above that is where we start needing steam. But it's a relatively small amount, and it's a low pressure steam, so it's not, you know, something that's, well, there's boilers everywhere. I mean, we even have one of our research centers. So yeah, it's very simple technology.
Okay, thank you. So another question for Stefano. This one is a sort of an expansion of the last question I asked you. This is from Mike Grant. So Mike asks, with hydrogen being a very light gas, can we contain enough heat in the hydrogen to heat the material, the iron ore in the reactor, without being extremely high temperature input gas? And for the H2 system, what is your aim input temperature for your process gas?
Well, first of all, in terms of containment, let me say, of gas, our plants are already designing works since ever, let me say, with the high pressure and with the very high content of hydrogen. So we have the proven experience at already 70%, the plant in, let me say, 2 million ton plant in Abu Dhabi is working more or less with 70% hydrogen. This is already proven. The sealing system works very well. In terms of distribution, high pressure definitely allows a better distribution. With the low pressure, we see a tendency of a light gas to stay more on the walls, let me say, of the reactor. With the high pressure, we create a better distribution inside the reactor. And finally, for temperature, again, the temperature from the process gas heater is lower than the one we use from a typical zero reformer scheme. There may be oxygen injection again to enhance kinetics. This is let's say a very well-known balance, thermodynamic balance.
All right, thank you for your answer. So I have one more follow-up question for both Vincent and Stefano, and you both touched on this briefly, but for converting to hydrogen iron making in the future, is your plan primarily to use pipeline hydrogen, or do you plan on designing DR plants with integrated hydrogen production systems should those become affordable and available? So Vincent, if you can go ahead first, and then Stefano.
Sure. So in one of the slides that I showed, so for the 100% hydrogen case, we're really we're looking at it both ways, because realistically we don't know how energy is going to be distributed in the future. Some people think that energy is going to be distributed via electricity. Some people are going to view it as being distributed by hydrogen, and we're not in a position to make the decision for all the countries in the world on how they're going to distribute energy. So we kind of prepared for both solutions, and the advantages and limitation of both. But it really, it's a matter of what is available at the plant side, and then it could be either coming a hydrogen from a pipeline, or if electricity is available, the hydrogen can be generated on site. And like I said, there's pros and cons. The advantages of having the hydrogen generation on site, so either piped into the loop, kind of semi-external if you want, or directly integrated in the loop, is the possibility of integrating some of the sub-circuits together. Especially things like water, for example, could be recycled, because the product of direct reduction with hydrogen will be water, and that's what you need for electrolysis. So obviously there are advantages to do that, but again, that requires a huge amount of electricity on site. So now you're talking about distributing a huge amount of power to a steel plant. So again, it's a function of what's available.
I will add that I fully agree with Vince, but I will add that the decision will be more based on a regional scenario. We can see that, for example, in Northern Europe, definitely the trend is to have a network of a hydrogen distribution. You may read it in Holland, Germany, let's say that part of the world is much ahead for hydrogen distribution. While in other regions, think about the MENA region, definitely it will be more on-site production of hydrogen through renewable resources. So again, for a DRI plant, it's a matter of opportunity, but from the technology itself, again, both technology, we just need the feed of hydrogen.
All right, thank you both for your answers. So we are out of time for questions. So I want to thank the panelists and attendees. If we didn't manage to get to your question, I apologize. I do encourage you, if you have further follow-up questions, please contact the presenters via email, and I'm sure they will be happy to discuss it with you. So at this point, I'll hand it back over to Dr. Pistorius.
Thank you very much, Zane. And all that remains for me is just to thank everybody involved, our upwards of 300 participants. Thank you for taking the time to listen to this both interesting and important topic today. Great thanks to our panelists for your presentations, especially to Jose, who really was the original instigator of having this presentation. As Zane mentioned, we plan to have a series of these, at least 2 more, focusing on other aspects, including hydrogen generation So please look out for those emails. Anna will be sending those out shortly. So thank you very much and have a good day further.
Thank you.
Thank you.
Thank you.
Yes, thank you all.
And here's a list of a few other upcoming webinars that we have over the next few days. So thank you all again and hope to see you at the next AIST webinar.